Okay, so lecture 35 is on Atwood's machine, which I've drawn a small picture of here. We're not actually going to solve this. This is in your problem sets, but I'm going to give you hints on how to solve it. But let me state what the Atwood's machine is all about. This is a device that was originally used, I think, to measure gravity, okay, what the gravitational acceleration is, okay?
It was used to spin wood.
No, and so what it is, it's basically two masses, not necessarily equal. They're usually different. Otherwise, you would get no acceleration. And they're connected by a piece of unstretchable rope, right? You're going to get the least stretchy rope that you can get, right? And it's wrapped around a pulley, okay? And so you can see physically what's going to happen, right? If M2 is greater than M1, right, then you're going to accelerate. This will accelerate downward, right? This guy will accelerate upward, right? If the weights are pretty close to each other, the acceleration will be rather small, okay? And that's where the advantage comes in. It's a little bit like what Galileo did with his inclined planes, right? He slowed gravity down so he could make more careful measurements, right?
Yeah.
And so you're doing the same thing here. You're kind of slowing down gravity, okay? But you're going to be able to figure out what it is. So you measure these accelerations, and that will help you figure out what the gravitational acceleration is. And that was the purpose behind it. But again, we're not going to solve this problem. Instead, what we're going to solve is a related problem. And this should give you some insight into how we will solve the Atwood's problem, Atwood's machine problem. I don't remember what year it was built, but it's George Atwood, I think, is the builder of the machine. It was probably 1780 or something like that. So here's the problem we're going to solve. Put a pulley here. There we go. So let's assume that this is a frictionless table, okay? And what we've done is we've rigged up a pulley system, right, like this. So we've connected this mass M1 to this mass M2, okay?
Yes.
And just like with Atwood's machine, we have a line which we'll assume is not, you can't stretch it, so it's not elastic. And we'll assume that its mass is negligible, so it doesn't contribute anything to the problem, right? Because remember, if it did have mass, then the tension that you would feel here and here would be different. But if the mass is negligible or zero, then we can assume that the tension 1 felt by body 1 and tension 2 felt by body 2 are equal and opposite, okay? Just like they are here, okay?
Yeah.
So another thing that we'll have to take into consideration in order to solve this problem is the fact that the acceleration of body 1 is related to the acceleration of body 2, right? You can see it. And same thing with Atwood's machine, right? If M2 is accelerating downward very quickly, right,
Yeah.
then mass 1 will be accelerating upward at the same rate. And the same thing in this problem here, okay? So this is like Atwood's machine light, which is why I'm going to work this one out, and I will leave Atwood's machine for you to solve, because there's not that many of these dynamics problems that I can come up with that are interesting, and this is probably one of the more interesting ones that's not overly burdened with complexities, okay? Let's write our assumptions down for starters. I'm going to assume the magnitude of T1 is equal to the magnitude of T2, which is equal to some scalar value T, okay?
Okay.
And the acceleration of 1, which will be in this direction, right, is the magnitude of that will be equal to the magnitude of the acceleration of 2, which we will just call A, okay?
Yeah.
Make sense?
Yes.
So these are what we call constraints on the system, and that if we didn't have these constraints, then this would be unsolvable, okay?
Okay.
So I think the first thing I'd like to do is let's deal with, and we're going to call this our x direction, and this our y direction. That's a terrible x, okay? So this is the positive x direction. This is the negative y direction, okay?
Okay. So
we have two bodies here, right? And a free body diagram requires us to isolate one of these bodies, okay? So if we want to consider the system, we've got to isolate each body one at a time, okay? So we'll say, for body 1, okay, that's this guy here. Let's draw a free body diagram for it. Well, we have the normal force and the weight. They're completely canceling each other out, right? It's a balanced force. So there's no acceleration in the y direction for body 1, right?
yeah.
So the sum of the forces of body 1 in the y direction is equal to 0. What about in the x direction? Well, here the sum of the forces in the x direction, right, will be equal to the mass of 1 times the acceleration of 1. Now here we're going to, because it will be accelerating in this direction, we know that that's positive, okay?
Okay.
So it's equal to ma. Now what is the sum of the forces acting on this body? Well, there's really only one. That's the tension, right? Also acting in the positive direction. So here we have that the tension is equal to M1A. Now let's look at body 2. This time, again, we have a weight and we have a tension, T, right? Now in the x direction, there are no forces in the x direction, okay? So there's no acceleration in the x direction, so we'll have a 0 equals 0 kind of thing. So I'm not even going to write anything down for that. But in the y direction, right, the sum of the forces in the y direction for body 2, right, this is M2, oops, M2, this would be M1, will be equal to the mass of body 2 times the acceleration, but this will be in the negative direction, right, because it will be going downwards, yes?
Yes. Yeah.
Do you think it's possible to set up a contraption like this where the acceleration is going up?
Yes. However.
How would we do that? Any answers on that? Well, I can imagine if somebody pulled on this, right? If they applied a pulling force to M1, then you could cause M2 to accelerate upwards, right?
Yeah.
But there's no set of masses that I can choose, right, that would cause M2 to accelerate upwards, okay? We're assuming this is a frictionless surface, okay?
Okay.
So if we chose, really heavy M1, would that cause M2 to accelerate upwards? No, it would not, right?
It would make M2 stay.
No, it wouldn't balance it out. There's no friction. So M2 will still feel an acceleration due to gravity downwards, okay?
The field is still staying.
Now with friction, yes, right, you could cause M2 not to move. You just have to make sure that the frictional force, which we haven't gotten into yet, was big enough to keep M1 from moving at all. But M1 will always feel a pull in that direction, right?
Yeah.
As long as there's a mass here. Doesn't matter if it's less than or greater than or equal to the mass, it's going to feel a pull. And on a frictionless surface, that means it will always accelerate to the right.
Okay, yeah.
Yeah, the only way you could get it for M2 to accelerate upwards is if somebody pulled on this on M1 that way. Okay?
All right.
So it's different than Atwood's machine. Atwood's machine, the direction of the acceleration will be determined by which one is greater, M1 or M2. Okay?
Okay.
Or if they're equal, there'll be no acceleration. Okay, so we've got that the sum of forces in the y direction for body 2 is equal to minus M2a. Now we have to enumerate these forces, and what do we have? We'll have a tension, T, which is in the positive direction, plus the weight, which will equal minus M2 times A. The weight, of course, is minus mg. So this becomes T minus mg, where m is m2, equals minus m2a. Okay? Now how do we solve for these things? Well, here's the trick, and this will help you out with Atwood's machine, okay? If I take this equation from body 2, and I subtract it from this equation for body 1, right? Let's solve for the tension in this equation. So this one would say that the tension T is equal to m2g minus m2a, okay?
All right.
And so if I add that to, we'll call this equation 1, and we'll call this equation 2. And so 1 minus 2, what does that give us? That gives us T equals m1a, and T equals m2g minus m2a. If I subtract these, right, T minus T, that'll be minus this. So minus this, minus this. Minus a minus is a plus, right? So I get T minus T is 0. M1A minus M2G is, well, really it's M1A plus M2A minus M2G. I should have collected like terms, right? So move this over here, right? And this will just have a 0, right? So we have M1A plus M2A. Well, that's just M1 plus M2 times A. And here we have minus M2G, right? And that's equal to 0. And so I can solve for acceleration A, okay? First I'll move M2G over to the other side of the equation, and I'll get that A, the acceleration, is equal to M2G divided by M1 plus M2. Okay?
Okay.
So that's the acceleration, and then I'll move the G outside. So you see it's this ratio of the mass M2 to the total mass, M1 plus M2. Sorry, this one here. So that's the acceleration that we'll get. It's the ratio of M2 to the total mass, M1 plus M2. Okay?
Okay.
And so if, for example, what if M1 was really light? What if M1 was basically 0? What would we expect? Let's say that there is no M1, right?
Yes.
What do we expect M2 to do? We expect it to just fall, right?
Yes.
So if M1 is 0, we get M2 over M2. Well, that just cancels out, right? That's just 1. So we get the acceleration is equal to G. Okay?
Okay.
So that makes sense, right?
Yes.
What else could we do here? We could consider the case where M2 was very, very heavy. and that would basically give us the same thing, right? We completely ignore m1, because if m2 was very large, right, then what would we say? We'd say the acceleration is equal to m2, which is a really large number, over m1 plus m2 times g. But if m1 plus m2, if m2 is very, very big, that's basically saying m1 is 0 again. And so this is just approximately m2 again, right?
Yes.
And so for very massive m2, it just behaves like it's free falling, right?
All right.
I suppose you could have the other case where you had a very heavy m1 and a very light m2. We don't want to make it 0, okay? Because if we made it 0, that would say there's no acceleration, and that would be like, well, if it's 0, there's nothing to fall, so there is no downward acceleration. But let's let m1 be very big, much, much greater than m2, right? What's the acceleration going to look like? Well, m1 plus m2, since m2 is very small compared to m1, this will be like approximately m2 over m1. So we have a very small number over a very big number times g, right?
Yeah.
So we'll have a very small acceleration. So if I have this a very heavy object and this is a very small object, even though there's no friction, the acceleration downward will be very slow. Okay?
Okay.
We're not done yet, though. We got the acceleration. There's one other thing that you'll need to be able to solve for to get the tensions in the Atwood machine, right? What's the tension in the line? Well, you could, for example, instead of subtracting these, add these. Okay?
Okay.
And that you could solve for the tension in that case. The problem is that you're going to have a quadratic equation to solve, and that's going to be a pain. My suggestion is that once you have the acceleration, let's just use it in the easiest of these two equations that we can find to find out what the tension is, because we can either use this equation, equation 2, tension is equal to m2g minus m2a, right?
Yeah.
Or we could use it in equation 1 and see what the tension is equal to. Let's do it in equation 1. That looks easy, right? So from equation 1, we get, and we'll call this equation 3, so 1 and 3 gives me that the tension T is equal to m1 times A, but A is just m2 over m1 plus m2 times g, right? So that gives me m1, m2 divided by m1 plus m2 times g. Okay?
Okay.
And that will be the tension that we have. Okay?
All right.
And so you can use the same strategies that I used here to solve the Atwood machine in a pretty straightforward manner. Okay? I don't think it's that much harder, but you could consider this a warm-up question.
Okay.
All right? So that's the Atwood's machine.